Oh, maybe not, because that's only on the computer. That's right, because I'm running the Luma on the computer. Okay. Yes, I'm transmitting the talk live online to a couple of my students, and I'm also recording it at the same time, because online students usually have a problem that they can't be all in the same place in the middle of the day at the same time. So, you know, most likely, even though there are just 2 people here right now, there are going to be a whole lot more who are going to look at the recording later. So I'm going to do this on my separate laptop here, and if there's a question from my online folks, then I'm going to, is it okay if I interrupt you? And,
sure.
Okay. Yes.
When will this be?
As soon as I open up the link. I mean, the recording just takes a couple of minutes to save it, and then I just have to click and open the link and send out the URL.
Cool.
All right. We can get started.
Okay.
Okay.
So I was going to begin at top by saying on Thursday of this week, the satellite will be launching in space, but the launch has been delayed. This is an astronomical telescope, NuSTAR X-ray telescope, and X-rays don't make it through the Earth's atmosphere, so to see things in the universe in X-rays, you have to put it up in space. There's a problem with the launch vehicle. They're testing new software for the launcher, so it won't happen this week, but within a couple of weeks probably.
What is will be another launch?
It's done by a private company called Orbital. Well, let me show you. This is the type of launch vehicle. It's called a Pegasus launcher. It's a relatively small launch vehicle. It kind of looks more like an airplane than it does like a space rocket. It's carried to about 40,000 feet, attached to a specially equipped Lockheed L-1011, and it drops off, and the engine lights, and it boots up into space. This launch system is made for payloads less than about 1,000 pounds, and you can see there's 3 rocket stages here. First stage motor, second stage motor, third stage motor. Payload is not shown. It's a pretty reliable launcher, so the thing should make it into space safely. And if it does, this is what it'll look like if properly deployed in space. And there's a reason why it's got this huge deployable mast in the middle. When it's launched, this will all be all together, and then this mast will be deployed or remote controlled. The reason that it's got this huge mast ultimately has to do with the fact that it's an imaging telescope. An imaging telescope makes a picture of what it's looking at. Not all telescopes image. Some telescopes simply measure the rate at which light energy is coming from the source, or make a spectrum of the light energy coming from the source. An imaging telescope makes an image of what it's looking at, like our eyes do. I can see all you because there's an image formed by my eyeballs, and that is being shown to my brain. And the way you image is you focus light. This is supposed to look like the cross-section of a bowl-shaped mirror, and there's light coming from an object off to the right that's being observed. Reflects against the curved surface and forms an image on the screen. And I can show you that this actually works. Relatively bright. So here's a bowl-shaped mirror. I was hoping there'd be a window in here.
Oh.
The window is usually right now. You know what? Shut off all the lights for a second. And now shut them all off.
Oh, off.
Because then the screen will be relatively bright. And I can form an image. See that?
Wait a minute, where are you?
So, let me shut it.
Oh.
And I'm putting you see this. Yes, the focus is here, well, roughly. But there's no mystery about this. Piece of paper, a curved mirror, and makes an image.
Can you repeat that for the camera right here?
You can see there's an image of the screen formed on this paper.
Oh, I think they can probably vaguely see it now.
Okay.
Yeah, those light structures.
Yeah, I didn't think
Yeah, that's an image of the screen. Okay.
Okay.
Okay, yeah, cool.
So, So you have to focus light in order to make an image. Our eyes don't use reflection off the curved mirror. Our eyes use refraction through a transparent lens. And that's the way a camera works. In front of a camera, there's a glass lens as the light passes through the curved surface. It refracts, focuses on a plane, which instead of being a piece of paper, is an electronic signal that kind of freezes the image, records it digitally, and emails it to somebody. So that's the way an imaging system works. And light is particles. They're photons. Photons are emitted by matter. Nearly all objects emit light all the time. You and I are emitting lots and lots of photons every second. And so is everything else in this room. You may wonder how an inanimate object like this desk emits light. It's because everything is emitting light. So this thing's absorbing photon energy as fast as it's emitting. But so are you and I. About everything emits light all the time. And photons come in a huge range of energy. And the amount of energy in a photon depends on the thing that's doing the emitting. For example, the hotter an object is, the higher the energy of a typical photon that it emits.
Frequency would generate more, something super high frequency X-ray.
Right, that's right, and that's what this is leading to. So here's a photograph of a boy, and when you and I look at each other, we don't see luminance. The light that we see from each other is light coming from another source, from the hot gas in the light fixture source from the sun, and it's bouncing off of so we can see them. But we're also emitting light at a couple of hundred watts, and the reason we don't see it is because the energies of the photons that we emit are lower than the range to which we can sense. We call this infrared light, and what we see we call visible light. We call it that because it's visible to us. But this is what a person looks like. This picture was taken with an infrared camera. It's got a detector in it that detects infrared photons in a similar way to the way an optical camera, a regular camera, detects visible photons. But the sun is a good bit hotter than you or me. It's about 20 times higher temperature than you or me. And as a result, the typical photon that it emits has about 20 times the energy that the typical photon that you and I emit. It also emits, every square foot of it also emits a lot more infrared photons like you and I emit than every square foot of me. But it mostly emits energy in what we call visible light. And in fact, our eyes are sensitive to that range of energies because that's mostly what the sun emits. Now you might also say, well, are there hotter objects that emit even higher energy photons? And the answer is yes. This is an artist's depiction of the region around a black hole. And black holes are really dense objects that have very strong gravitational fields. And if there's matter near them, then the gravitational field can interact with that matter in a strong way and compress it and swirl it, heat it up to tens of millions of degrees, and cause it to emit very high energy photons. And the X-ray part of the spectrum is real high energy photons. This is supposed to look like a matter swirling around in a disc-shaped thing, and jets of material that tend to come out of these black holes. So black holes are one of the things that they want to observe using NuSTAR because a lot of them are strong X-ray sources. They're only X-ray sources if they're interacting with material around them. But there's evidently enough of them in our galaxy doing that because we know that it's these strong X-ray sources out there. Another thing is a supernova. Supernova is another very energetic process. This is a galaxy outside of our own. If you could go a long ways outside of our galaxy and look back, it might look something like this. Now, these individual stars here are stars in our own galaxy. We have to look out of our own galaxy to see this other galaxy of hundreds of stars. There are no stars in here that are actually seen that are resolved from the rest. They're not big enough to stand out among the rest, except this one right here. That's a supernova. Some stars explode, and when they do so, they emit energy at a rate that's billions of times normal. And and that is a supernova in that galaxy. So they're so bright, they can be seen from extreme distances, and they can outshine the light of an entire galaxy. Supernovae are another thing that they want to study using NuSTAR because there's energy that material in NuSTAR emits that tell us things about what goes on in the actual explosion, which there's a lot about that we don't understand. So I'll talk a bit more about how we can learn more about supernovae and black holes by studying. So this is a supernova remnant in our own galaxy. This explosion was actually observed about 1,000 years ago. It was seen as a bright star in the sky for a couple of months. It was actually observable during the day. That's how bright it was. So this is one of the more recent ones in our galaxy. These things occur about every century or so in a typical galaxy like our own. Okay, now, before I talk more about the things that they want to look at using NuSTAR, let me talk a little bit about how it focuses light, because that's pretty interesting in itself. One of the ideal shapes of a curved mirror to use to focus light is called a paraboloid. Now, probably some of you have heard of a parabola, right? So what a parabola is the graph of a quadratic function, right? And this is a simple quadratic. This is just y is equal to x squared. And it turns out if you take this curve and rotate it around the y-axis, it'll sweep out a two-dimensional surface, and that two-dimensional surface is a paraboloid. And if you make a physical thing like that, and make the inside shiny by covering it with aluminum or something, photons coming down, traveling parallel to the y-axis, when they reflect off there, they'll all pass through the same point. And that point is called the focus. So a paraboloid is a good bowl shape to use to focus light in a telescope. Now this is a pretty shallow dish, right? You might imagine that this is this much of a paraboloid. It's probably not actually paraboloidally shaped, but it might be this part of a parabola. Now, the thing about X-rays is they won't reflect at high angles. These are coming in nearly perpendicular to the surface. You can't refract X-rays at all. Not this thing, X-ray light. And they'll only reflect at very low angles where they're going almost parallel to the reflected surface. So this kind of thing is not going to work. I mean, they're moving almost perpendicular to the surface here. And even up here, they're moving at low angles, but not low enough. So how can you focus X-rays if you can't use this kind of shape? Well, anyway, think of a way. Well, this is the parabola graph farther up, right? Now, there is these places up here, a photon traveling parallel to the y-axis is going to be moving at a low angle with respect to the surface. So if you rotate this curve around the y-axis, you get a paraboloid, a very deep bowl, and part of it, at least, will have the capability to reflect X-rays. Now, all the lower part won't. So if you get rid of it and just keep the part up here, what you're going to have is like a tube that's tapered, right? A section of a paraboloid that's capable of reflecting X-rays. So you'll have this section up here. And so that's what it's hard to see, but I just saved that part of the parabola, right? Now imagine, that's a ring around there, right? That's the paraboloidal section. Now, a photon coming down the axis of this thing, this is what it's going to see. It's not going to see very much reflective surface, right? Only a small fraction of the photons that come into a telescope with a reflector like this are actually going to focus. Not going to be a very sensitive telescope. So is there a way to increase the focusing area? Well, it turns out there's more than one parabola that has the same focus. And I grabbed this on Excel. It's kind of hard to see, but not all of them go through the origin there. The ones that are inside the bottom part is a little higher up, and I adjusted them so that they all have the same focus. Okay, the same point down here is the focus. So here you have a whole bunch of these coaxial paraboloidal things, and if you save just the part that can reflect X-rays, just these sections up here. So imagine all these coaxial rings of paraboloidal sections. Now a photon coming into the front of the telescope sees a much larger collecting area. So you can imagine a photon coming down vertically and just make it between two of these sections, reflect off, and then head down toward the focus. And it's the same focus for all these paraboloidal sections, so you can focus light this way. Now, one of the downsides of this is that you wind up with a really long focal length, right? The distance between the optics and the focal plane is really large, and that's undesirable for a number of reasons, not the least of which is it makes for an ungainly telescope that's difficult to point, right? So is there a way to shorten the focal length a bit? Well, the mathematicians give us an answer to that, too. There's another curve called a hyperbola. Anybody ever heard of a hyperbola? The graph of a different mathematical function, right? So it's another one of the conic sections. And that has two foci instead of one focus. And take this curve, rotate it around the vertical axis, you get a different bowl shape. Silver that thing, and a photon that's already headed toward this focus, when it hits that, will go to the other focus. So if you have light that's already being focused by some sort of focusing rig, when it hits a hyperboloidal mirror, it'll go toward a focus and effectively short the focal length by a factor of a couple. And so this is the way they build X-ray telescopes. And this is the way, for a couple of decades, X-ray telescopes have been built like this. You have these coaxial paraboloidal sections and coaxial hyperboloidal sections, and down here is the focal plane. The focal length of NuSTAR is still about 7.5 meters, which is probably shorter than the length of this room, but it's long enough. And that's why that extendable boom is on there, because the optics have to go way out in front of the focal plane in order to focus the light. And I think I have a picture here of, this is the NuSTAR optics. And there's 133 of these concentric hyperboloidal and paraboloidal sections that do all that focusing. There's actually two of these, because there's several instruments on NuSTAR that they want to use at the same time. You can only put one instrument in the focal plane at a time. So that it's essentially two parallel telescopes. Looks like a pair of binoculars or something. This is the detector. This little plane right here is where the image forms. And it's an X-ray detector made by a company that makes X-ray detectors for all sorts of scientific research. And the neat thing about it is this kind of detector doesn't need to be chilled down to a low temperature to operate. Some detectors, you need to chill it down to a couple of degrees above absolute zero, and so you need a coolant system that has coolant that will eventually run out. Well, NuSTAR, this thing will operate at the ambient temperature of the spacecraft, and so it will last a long time. The nominal mission length is like 2 years. They've got the first 2 years planned, all the observations are figured out. But if everything is going well after that, this thing could be observing objects for much longer than that, for many times that. So this will probably, if everything goes well, it will have a long life. Okay, now let me talk a little bit more about what it's going to observe. This is, one thing I didn't mention. The distinction of NuSTAR, it's the highest energy imaging telescope ever. In other words, it'll make images in higher energy photons than any previous telescope. There are telescopes that detect higher energy photons, but they aren't imagers. And imaging is a very important thing because you're focusing light, you're concentrating it from a given source, so that makes a very sensitive telescope, and you wind up with an image, right? You wind up with a picture of the sky, which picture is worth 1,000 words. This is a map of of our galaxy, basically a picture of our galaxy at the energy range that NuSTAR is sensitive to. Now, you might say, well, I thought we didn't have any imaging telescopes that can. This was made by a non-imaging telescope, and it takes a lot of observations and scanning across the sky to build this image, and it's not a very deep image. In other words, it's not sensitive to really faint sources. But to show you, this is actually a fairly large section of the sky, and to show you that, I want to introduce you to the galactic coordinate system. If you could step outside of our galaxy and look back, this is an artist's conception based on a lot of observations about our galaxy. And the artist actually put the Earth right here. That's where the solar system is. So that's where we are in this painting. But to explain the galactic coordinate system, I couldn't really do it with Earth there, so I'm pretending the Earth is over here for a second. Okay? So we're really like right there, but same difference, right? And the galactic coordinate system is like the Earth's geographic coordinate system. Our geographic coordinates in Atlanta, or our longitude is about 85 degrees west, and that means start at the origin of this, which is a point on the equator off of Africa, go around the equator until you come to a point on the equator that's just south of us here, and that's about 85 degrees around the center of the Earth, right? It's an angle around the center of the Earth. So our longitude is 85 degrees west, because you're going west around the center of the Earth. And then our latitude is about 34 degrees, in other words, an angle up from, with its vertex at the center of the Earth, up from the equator to this place in Atlanta. So it's two angles. It's like a spherical coordinate system, and it's two angles. That's how the galactic coordinate system works. It's centered on the Earth. The direction towards the center of the galaxy is the origin of the galactic coordinate system. That's how these galactic astronomers have set it up. And then we live in this kind of disc-shaped galaxy. So the longitude measures around a circle in the plane. So 180 degrees galactic longitude would be the direction away from the center of the galaxy, right? And then the latitude would be out of that plane. So the direction straight up out of the plane of the galaxy would be 90 degrees galactic latitude. So, yes?
Of the object that but would it be any difference in the solar system and the reference point instead of our planet?
No. Because, you mean like the sun or something as the center of this? Not much, because the galaxy is billions of times larger than the solar system. Yeah. Yeah, what they mean is the solar system. I mean, if you zoomed in not to get to the solar system, I mean, the solar system, even the orbit of Pluto, would be invisible on this image. Our galaxy is so much bigger than the solar system. We basically, I guess it's essentially centered on the Earth, but okay, so given that coordinate system, now this picture is labeled with galactic coordinates. So you can see there's 0 longitude, 0 latitude. So that's the center of the galaxy right there. And then longitude is horizontal, so you can see the plane of the galaxy along here. So you can see there's a bunch of point sources of these high-energy X-rays. They're evidently in our galaxy because they're concentrated along the plane of the galaxy. And they're bunched more towards the center of the galaxy. So there's these point sources of X-rays in our galaxy. Many of them are probably black holes. And it's this kind of thing that they want to find more of using NuSTAR. And so they'll be able to resolve these and find much fainter sources than the faintest ones in here. Probably a factor of 100 fainter than the faintest ones in here. This is an image of the center of the galaxy. This thing right here, that means Sagittarius A star, that is a massive black hole, 4 million times heavier than the sun, that's at the center of our galaxy. And it is not a strong X-ray source. There's X-rays coming from that region, right? But It's not a super strong X-ray source. But this is a simulated image of what a NuSTAR image of that region might look like. So, and you can see lots of these little sources right here. This is what people are hoping and expecting to see based on how much X-rays are coming from there that are not resolved into sources, right? So you can see the improvement in resolution here, in ability to resolve sources. So, and many of these may turn out to be black holes. Black holes are important because they're evidently the remnants of exploded stars, and very heavy exploded stars. And so knowing more about their distribution in our galaxy and their populations in our galaxy tells us more about the history of star formation and star death in our galaxy. And this extremely heavy one at the center of our galaxy, these black holes, some of them are, they call them supermassive black holes because they're millions of times the mass of a typical star. And they apparently are the result of the agglomeration of many smaller black holes. That's another thing we don't know much about, how that works. So I'll hopefully find some of this stuff out there. Now, some black holes, as I say, are these supermassive black holes, and the one in our galaxy is not interacting strongly with material around it. There simply isn't enough material around it to make it heat that stuff and make a real strong X-ray source. But in some galaxies, the supermassive black hole is. And when there is material being affected by the huge gravity of the supermassive black hole, you call that an active galactic nucleus. And in fact, the first evidence for black holes were the observation that some galaxies have these very bright energy sources at their center, and people figured for a long time that they are these enormous black holes, but now that's been pretty well shown that that's what they are. This is a galaxy called Centaurus A, and most of this is visible light picture, but this right here is they've superposed a radio picture on there. This is material that's being ejected from the center of this galaxy by the activity of its active galactic nucleus, and that's stuffing its radio energy as it extends out. Now, most of these active galactic nuclei are seen in galaxies at enormous distances from us. This one is probably the closest one to us in space, but most of the galaxies near us, they evidently have supermassive black holes because they are affecting their environment in a way that suggests very strong gravity, but they're not active like this. They're not heating material right near them. But if you look at extreme distances in space, like nearly all the way to the edge of the observable universe, you see a very large number of these active galactic nuclei, which implies, light has a finite speed. So the farther away we look in space, the farther back we're looking in time. And if you look at nearly the most distant places that you can see in the universe, you're seeing those objects as they were in the early history of the universe. So the fact that we see active galactic nuclei at extreme distances means that early in the universe, these supermassive black holes in galaxies were more often interacting with material than they are now. Maybe they've run out of material to interact with. And and this is of interest to astronomers because almost as far away as we look, we see these active galactic nuclei, which means these supermassive black holes existed even at a very early time. They had to have formed at some point, but they evidently formed fairly quickly in the first billion years of the history of the universe because we can see the evidence of their activity at extreme distances, which means they were around even very early on. And a lot of these should be detected. Let me show you this. This is a spectrum of, this shows the intensity of the background radiation coming from all parts of the universe. And this is energy. This is a logarithmic scale. That means 1 kiloelectron volt. A visible photon that we see has a couple of electron volts of energy in it. An electron volt is the unit of energy that they use in physics. But the ones that we see have a couple of electron volts. A kiloelectron volt is 1,000 electron volts. So 1 kiloelectron volt is maybe 500 times the energy of a visible photon. And this is 10 kiloelectron volts, 1,000. So there's high energy photons coming from all parts of the universe, and the peak, the energy that they're coming in most strongly at is between 10 and 100, what's that, about 20 kiloelectron volts, something like that. That's thought to be coming from these active galactic nuclei at extreme distances, but we don't know because we can't resolve them yet. And it's thought to come from ones that are obscured in visible light. So these active galactic nuclei can't be seen with a visible telescope, but X-rays will make it through the stuff that the visible light does not. So this indicates that there may very well be a lot more of these active galactic nuclei that we don't know about, and that's one of the things that. Yes, this is made with an X-ray telescope, a non-imaging X-ray telescope. We just know that there's this background of X-rays coming from distant space.
For instance, the source will be out the thousands of source.
Right, we don't know the source. We just know it's coming from somewhere because there's never been an imaging telescope which can resolve where it's coming from. I mean, you can point a telescope, if it doesn't have any ability to resolve the sky, it can tell you there's something coming from a region, but it can't tell you where exactly it's coming from. Oh, and I forgot. What?
How does gamma burst sources play into this?
Gamma rays are even more energetic than X-rays, and gamma ray bursts are bursts of gamma rays which come from extremely distant galaxies, and they've been shown to be exploding stars, particularly energetic exploding stars. And there are telescopes in space which detect those bursts. There's one called SWIFT, which has 3 telescopes on board. There's a gamma ray telescope, an imaging X-ray telescope, and a visible UV telescope, so it can image a thing, from the visible all the way up to the gamma ray part of the spectrum. But the gamma ray telescope is not an imaging thing, which is why they have the other instruments on board. When a gamma ray burst is detected, this thing has the ability to locate the direction, and the thing can turn over and point these other 2 telescopes at it to find out exactly what is bursting. And it's because of a couple of instruments like that that we now know what gamma ray bursts are coming from. They're coming from these exploding stars. Because these other, like a visible telescope, technology in visible telescopes has reached a point where we have very high resolution, and we can see the universe in fine detail, so they can locate these sources before they go dim again. Chandra is another X-ray telescope. It's a great big X-ray telescope that's up in space right now, and this is its sensitivity range. It goes from between 1/10 and 1 keV up to about 1 keV. But NuSTAR will extend that up to about 80 keV, and that's obviously an important part of the X-ray background spectrum. I'm sorry? Yes, NuSTAR will now cover this energy range.
I mean, this order, the extra drive. We need another instrument also to be able to monitor this region also. So we have Chandra here, we have NuSTAR.
Oh, and you got to go over here. Yes, that's right. I don't, as you go to higher frequencies, it's more and more difficult to focus the photons, and I don't know if it's possible to focus gamma rays, but I think. Why not? Because it has to do with the index of refraction, and an index of refraction is it's the way matter interacts with photons depends on the frequency of the photon. And the reason a prism separates light into its colors is because the index of refraction is a function of frequency, so the blue light bends more than the red light. Well, in the X-ray part of the spectrum, the index of refraction is such that it won't refract light at all, and it'll only reflect at low angles. It has to do with the index of refraction. I actually have a figure in here that I can show you at the end of it, which the index of refraction is a complicated function of frequency. It's interesting the way it works, but but that's the reason why most X-rays are absorbed in solid matter, but but you can reflect it at low angles. And the higher the frequency, the lower the angle that is the limit. Now, to look for these distant sources, what they're going to do, the NuSTAR has a relatively narrow field of view, and so you can't cover the whole sky. But they want to cover places which have already been covered by previous instruments, like this Chandra X-ray telescope, which is a very sensitive instrument. And there was a survey done a number of years ago called GOOD, the Great Observatories Origins Deep Survey. Great Observatories refers to 3 observatories in space. Forgot to turn that off. The Hubble Space Telescope, the Chandra X-ray Telescope, and the Spitzer Infrared Telescope. All 3 are these very large, very sensitive telescopes in different parts of the spectrum. And they were used together to survey a relatively small region of the sky that doesn't have very many galactic objects in it. In other words, a place where we don't see objects in our own galaxy, so you can look at very distant things. And you can see here's the Chandra field of this. There's 2 different places in the sky where they did this, and a south and a north field. Here's the Chandra field, and then inside that, wait a minute. Okay, the blue is the Hubble Space Telescope. It's 2 different fields that they overlap, and then this is the 6 fields of the infrared, or 6 or 8 infrared fields. In other words, they mapped at very high sensitivity, pointed the telescopes there a long time to see what sources turned up, because largely to find these extremely distant galaxies and their active galactic nuclei. And this survey suggested that there are a lot of these hidden active galactic nuclei that can't be seen in visible light, but will show up in high-energy X-rays. So this is one of the places, I guess both of these fields, are one of the places where NuSTAR is going to be used to make deep surveys to find higher energy sources than the ones that we know about so far. Okay, now supernovae. Supernovae is the other major kind of object that they want to study. This is an X-ray image of a supernova remnant in our own galaxy. And this is, I think this is Kepler's supernova. It exploded a couple hundred years ago, or it was observed a couple hundred years ago, or longer ago than that. But this is expanding shell of gas. They want to use NuSTAR to observe these recently exploded supernovae, ones that have exploded from a few years ago to a few thousand years ago. And the reason is there's material in there, radioactive elements, that are going to produce X-rays as they decay. And those radioactive elements come from the activity of the supernova and can tell us a lot about what happens inside a supernova. When a heavy star, this is what we think the inside of a heavy star is structured like near the end of its life. There's a lot of hydrogen, the most abundant element, and a bunch of helium inside that, a bunch of carbon, a bunch of oxygen inside that. Inside that is a bunch of silicon, and then at the center, a whole lot of iron, 1.33 times the mass of the sun in iron. Now, it's not solid iron, it's gaseous, right? Extremely hot. But you can see there's lots of this stuff. 1.7 solar masses, helium, 20% of the mass of the sun of carbon, and, you know, the sun is 1/3 of a million times heavier than the Earth. So this is a lot of material. According to our understanding of how the reason these things explode, when this iron is sort of depleted in nuclear energy. These elements are all formed by thermonuclear fusion. It's so hot inside stars that nuclei are slammed together and fused into heavier nuclei, and so that's why you get this succession of heavier elements toward the inside. Yes, extremely high pressure, high temperature, and high everything. So once you get a lot of iron doesn't have any more nuclear energy in it. So that builds up, and when it reaches a certain amount, it collapses, and that gravitational collapse releases a giant amount of energy, which is what causes the star to explode. Now, notice what's around it. A bunch of silicon. 0.17 solar masses of silicon. That's about 60,000 times the mass of the Earth in silicon. And that's right in the core of where the energy is produced. And it's thought that what happens is some of these silicon nuclei, silicon-28, same silicon that's on the Earth, is blown, no, I mean, not the same silicon, but the same isotope of silicon, is blown apart into alpha particles, which are like helium nuclei. Those are pretty strongly bound little groups of nucleons. And then these can shower onto more silicon. You put a helium core onto a silicon, you get a sulfur-32. Put another helium onto there, you get an argon-36. And then a calcium-40, titanium-44, chromium-48. All of these, or their decay products, are very common in high abundance in the solar system. And that suggests that it's this process that produced them, the inside the explosion of a star. Trouble is, up to now, it's been difficult to observe the products of a newly exploded supernova to see if that's what's coming out of them and how much. And it turns out, especially this one right here, titanium-44, it's a radioactive isotope of titanium, has a half-life of like 60 years. And when it decays into selenium-44? scandium-44, and it was an S word. And that scandium-44, due to its nuclear properties, spits out either a 68 keV X-ray or a 78 keV X-ray. So you point NuSTAR at one of these exploding supernovae, and you see these two emission features. That you see these X-rays at these two different energies. That's an indication of the decay of the titanium-44. So you can measure the amount of titanium-44 and also its dynamics. Is it moving toward you real fast or away from you? Is it, what is its physical state? Since this stuff is formed deep inside the supernova, that will serve as a tracer of what went on during the supernova. And that's something that nobody's been able to do before, to see these newly formed elements, because this serves as a probe of how that thing works. And there's a lot that we don't know about it. How, you can make models all your life about how this stuff works, but there's a lot we don't know about how this works, and we know we don't know because most of the simulations of supernova don't even explode. We know where the energy comes from, but somehow that energy doesn't get deposited in the right place to blow the star apart. So, and this is a computer simulation of a supernova, and you can see it's complicated. Seems to be complicated how it works. This is not. These simulations are inadequate in that most of them don't even explode, and so there's something that these models is missing, right? Or many things that these models are missing, which would be interesting to know how they work. And one of the reasons it's interesting to know this because the elements in the solar system, the relative abundances of them, are such that it appears that they come from these exploding stars. These heavy stars are the only places we know of where the elements, most of the elements we have in the solar system can be formed. They cook up those elements that I was showing you on that other diagram before they explode, and then when they explode, they cook up even more elements. And evidently that's where this stuff comes from. Yeah, most of these elements come from explosions of supernovae. So, this is our own deep past we're looking into here. And it would be interesting to know how this really works. Another thing that could be studied is this is the sun, and these blue dots are the locations of what are called microflares. They also produce high-energy photons. I mean, there's a number of other things which produce, quite a few other things which produce high-energy photons, like activity in the formation of stars in other galaxies. But one of the things they want to study is these microflares in the atmosphere of the sun, because the sun's hot atmosphere affects the Earth in a really profound way. It affects our weather, affects communications, and it's very complicated how it works. So not very well understood how it works. So that's another thing that this could be used to observe. Let's see, I think. Oh, yeah, this is that figure I was talking about, the index of refraction as a function of, here's the infrared part, is visible, ultraviolet, X-ray. The index of refraction has this strange dependence on, I mean, this may not mean much just looking at it, but in the X-ray, here is 1. This means that in the part that we're looking at, the index of refraction is right around 1, and that makes refracting them impossible and reflecting them difficult. But yeah, I think it just keeps on going up closer to 1. I'm not sure what it does in the gamma ray part of the spectrum, but asymptotic. I don't know. I think it's asymptotic because it's the way the wave phenomenon interacts with the motion of the material. I'm not really sure about what happens in the gamma part of the spectrum, but anyway, that's your answer to why it's difficult to reflect them. Okay, so anyway, hopefully in a couple of months they'll figure out the launch vehicle and launch the thing into space, and it'll make it and be deployed properly. And in a few years, we'll know more about the black hole population of our galaxy, know more about how supernovae blow up, and all kinds of other fun things. Is what? I don't know. I guess so. Well, NASA has paid for this. NASA does most of the, they paid for most of the space astronomy instruments. Is that right? Out of their budget, out of their science budget, comes the money for most of the astronomical telescopes that are in space. I think that's right. But this comes from NASA funding, and yeah, so it's the government, it's us, that's paying for this. Oh yes, yeah. This Pegasus launcher has been used, I think, like 25 flights in a row without blowing one up. The first couple of launches were it was kind of a stumbling start with that launcher back in the, and they blew up it was Gravity Probe A, I think, that got destroyed on a Pegasus failure. That was a science instrument, but I think they've had like 25 straight successful launches, so it's pretty reliable now. And
when NuSTAR is deployed, what will be off?
I don't know. I had that in my brain and it left. I don't know. It's not real high altitude because this launcher, you know, is a relatively small launcher, and yes, yeah. Space station's relatively low. That's 250 miles, yeah. So this is higher than that because space station has to be boosted every couple of months because there's atmosphere up there. Yeah, and this is a much smaller object, so it would decay even faster probably. But I'm almost certain that. Well, the higher up, the longer it takes. Yeah, right.
How long does it take to build?
That's a good question. How long has this been underway? These space astronomy instruments are usually, I mean, at least 10 years in the planning phases because this thing has to be designed, and you know, they're really sophisticated instruments. And of course, you have to plan the launch years in advance, and it just takes. I don't know when people first started planning for this, but it's been a long time. 70s that have been increasingly sophisticated, and but this one will image it, highest photon energies. Should be.
Was the original intent to put up in the shuttle?
Oh, is it? I don't know.
Was it Chandra?
Yeah, Chandra went up in the shuttle because it's so big. Its size was essentially limited by the size of the shuttle cargo bay. But this is, much smaller. It can go up on a Pegasus. I'm not sure what the trade-off is for that size. You know, Chandra is really sensitive, I guess, right? But yeah, lower energies. Yeah, it could be because I think the original launch schedule was like August of last year.
What is the launch date now?
It's undetermined because they wrote new software for the guidance system for the launch vehicle or something like that, and they haven't tested it sufficiently. It was going to be this Thursday, but I can let's see. I can show you how to find out. Is there some other color other than yellow? Well, let's see. No. Well, actually, since this is a not Wimba, I can bring up a browser, right? Actually, let's look at the website because maybe they've figured out a launch date now. So, it's thing on Grace. That's another interesting probe. So, www.nasa.gov, that gets you to the main NASA website, and then if you just go /NuSTAR.
So, and then slash.
Yeah, see, they don't have the countdown to launch because they don't know when it's going to launch yet. Oh, there's a media briefing. 9 a.m. Tuesday. Yeah, so it'll probably be a better talk than mine. It'll be the people that actually run this thing, so they know a lot more about it than I do. So you can watch, if you're interested, you can watch the media briefing 9 a.m. tomorrow on NASA TV. If you go to the main NASA website.
You just click on that link.
This is www.nasa.gov. If you scroll down here, it says NASA Television Watch Live Now. Click on that, and it'll bring up and you watch that live. NASA Television is like, I think it's 24 hours a day. You can watch it online. So 9 a.m. tomorrow, they got a briefing on this. I didn't know that. They might be talking about the rescheduling or something. But they might be talking about the science involved and all that. Yeah, I know. Yeah, they show all kinds of launches of, not only scientific instruments, but communication satellites and military satellites. And if you like to watch launches on TV, it's a good place to go. Okay, so that's about all I got. Yeah, thank you. Thanks for coming. Just right in an hour. Cool.